Hello everyone, how are you all? I hope you all are well. So today we are going to discuss about the numericals based on the defects of the solids. In the previous video we have already discussed about the defects of the solids. So if you want to check that, you can click on the I button. Now today we are going to discuss about the numericals. So first we are going to discuss about the numericals based on the metal deficiency defect. In the previous video we have discussed about the metal deficiency defect. So the numerical based on that can come in board examination. So that is very important. So let's start. Now the first thing is that analysis shows that nickel oxide is having a formula Ni 0.94O1.00. Calculate the concentration of nickel ion and nickel, that is Ni2 plus and Ni3 plus ion in the solid. You all know that in such kind of solids, the concentration of the nickel will be in a different valency present in the same solid. Like Ni will be existing as a 2 plus as well as 3 plus, and because of that only this type of the defect is created. So we have to find that what is the concentration of nickel ion, that is Ni2 plus and Ni3 plus will be present here. Now for solving such kind of a question we are going to use the oxidation number method, which you have done in grade 11. So let's see how. Suppose let's consider the amount of the Ni2 plus in the solid is equivalent to X. We'll be taking it equivalent to some variable, like we can take it equivalent to X. Okay, then the other one, that is the other one means the Ni3 plus, as the total amount you can see in the formula is 0.94. So the amount of the Ni3 plus in the solid will become equivalent to 0.94 minus X, because whatever the amount of the X is going to be there, except that the whole amount of the Ni3 plus will be present in the solid, that is 0.94 minus X, as the total is 0.94. Now oxidation state of the nickel here is 2 plus. So by using the oxidation number method means what we are going to do, we are going to we are going to multiply the concentration of the everything which is present in this solid with their oxidation state, and then we will be taking it their sum of the oxidation state equivalent to the charge present on the solid. That is a way of doing the numericals by using oxidation number method, like we used to find the oxidation number. So in case of nickel, the oxidation Ni2 plus, the oxidation number is 2 plus. So we will be taking X with a multiple of 2 plus. Now 3 plus is the another ion, that is Ni3 plus. So its amount is going to be the multiple of 3, that is 3 into 0.94 minus X. Okay, then one more an ion is also going to be present in this solid, that is oxygen. Oxygen is having the oxidation state of -2, and the amount of oxygen given here is 1. So it will be -2 multiplied by 1. Now the sum of oxidation state of the substance which are present in a solid will be always equivalent to the charge present on entire solid. Okay, so if you can see that the charge present on this entire solid will be equivalent to 0 because there is no charge. Now we have to simply calculate the value of X. Now 2X plus, if you multiply it, you will find it as 2.82 minus 3X minus 2 equivalent to 0. So we will be calculating the value of X here. So minus X will be equivalent to minus 0.82, or X value will be coming equivalent to 0.82. Okay, now we have to calculate this value in terms of percentage. So it means that the amount of the substance which is present there, we have to calculate its percentage. So Ni2 plus will be equivalent to 0.82 as we have calculated, as it is equivalent to X, divided by 0.94 multiplied by 100. So when we do the calculation here, the calculation is coming equivalent to 87.2%. Okay, so that is the concentration of the nickel ion which is coming here. Now we have to calculate the concentration of other ion, that is Ni3 plus. So we have to simply take its difference with 100, because we know the percentage of nickel ion, so we will be taking the difference from the 100, and that will be the concentration of Ni3 plus ion. So the Ni3 plus ion present here will be equivalent to 100 minus 87.2, that is coming equivalent to 12.8%. Okay, so that is how we have calculated the percentage of both the ions present in this solid. Okay, so we have to simply use the oxidation number method. Now similar question of that type. Analysis shows that iron oxide is having formula Fe 0.96 and O 1.00. Fe2 plus and Fe3 plus, the two types of the ions are present in the solid, so we have to calculate their concentration. So similar kind of question, let's start. Let us consider the concentration of the Fe2 plus ion as X. Okay, so we considered the concentration of Fe2 plus ion as X. So the concentration of Fe3 plus will become 0.96 minus X, as the total number of the Fe are 0.96. So X will be going to be the multiple of 2, and 0.96 minus X will be going to be the multiple of 3, and as oxygen is there, so oxygen will be going to be the multiple of minus 2 into 1, because the number of the oxygen is 1, and the whole multiplication will be coming equivalent to 0, because there is no charge present on the solid, so it is equivalent to 0. So when you calculate, it will become 2x plus 2.88 minus 3x minus 2 equivalent to 0. So when you calculate, minus x will be coming equivalent to minus 0.88, or basically x is coming equivalent to 0.88. So we have to calculate the concentration of Fe2 plus. As it is coming 0.88, it should be divided by 0.96 and then multiply with 100 in order to convert it into percentage. So when you calculate it, you will find it will be coming approximate 91.7%. Okay, so the concentration of the other ion, that is Fe3 plus, will be equivalent to 100 minus 91.7, that is coming equivalent to 8.3%. Okay, so that is how you can calculate the concentration of the different ions present in the same solid. So that is a way to solve these kind of the numericals based on metal deficiency defect. Now we are going to do the numerical based on the impurity defects. Okay, so that's it. Now we are going to do the numericals based on the impurity defect. Now impurity defect means that the certain type of a solid is doped with another ion or another compound. Due to the introduction of that compound, some vacancies may be created in the solid. So that was impurity defect. So here we can see the numerical, the NaCl solid is there and it is doped with, that is the introduction of the impurities is there, that it is doped with 0.001 mole percentage of strontium chloride. Okay, strontium chloride is the impurity which is introduced and its amount is 0.001 mole percentage. Okay, now you have to calculate the number of cation vacancies created due to that. So let's see, it's very easy because it's a simple unitary method we are going to apply in it, and we have to take care only one thing, that what impurities is introduced and what is the charge on the cation there, because if you know the charge of the cation, then you can only know that how much cation vacancies can be created with the help of that. So let's see. Now we know that strontium ion will be having a charge of 2 plus. Okay, so if we introduce one strontium ion, suppose one strontium ion we have introduced, then it is going to displace 2 sodium ion, because the charge on the strontium is 2 plus and charge on the sodium is plus 1. So it means to maintain the electrical neutrality of the solid, 2 sodium ion are going to be displaced. Okay, so when 2 sodium ion are going to be displaced, the space of one is going to be occupied by the strontium ion itself and the other is going to be left vacant. It means that one cation vacancy will be created here. Okay, so when one cation vacancy is going to be created, it is going to be created by the one strontium ion. Okay, so total number of cation vacancy in this case is going to be 1. One cation vacancy is going to be there of sodium ion. Okay, now suppose if we introduce 1 mole of strontium ion in the same solid, then it will create how many cation vacancy? 1 mole of Na plus vacancy. It's very simple because it is directly proportional now. As one strontium ion is creating one cation vacancy, so 1 mole of strontium ion will be creating 1 mole of sodium ion vacancy. Clear? Now 1 mole, as we all know, is equivalent to the Avogadro number, that is 6.022 into 10 raised to 23. So it means that 1 mole of strontium ion will be creating this much number of Na plus vacancies. Now we have to calculate that 0.001 mole percentage of if strontium ion is introduced, then how many cation vacancies are there. So now we are going to use simply a unitary method, but as it is given in mole percentage, so we need to convert this mole percentage into the fractional form. For that we need to divide the value with 100. So it means that 0.001 mole percentage, so we will be converting it into fraction by dividing it with 100 mole of strontium ion when introduced. Then how many vacancy will be there? 6.022 into 10 raised to power 23 multiple of this value, that is 0.001 divided by 100. Okay, it's like 1 apple cost 20 rupees. So what is the cost of 5 apples? So it's going to be the multiple of that. Simple. Then you can change it as 6.022 into 10 raised to power 23 multiply by 10 raised to power minus 5, because when you convert it, it will be coming like that. So the final answer is 6.022 into 10 raised to power 18. So this much Na vacancies are going to be created when this much mole percentage of the strontium ion is introduced. Okay, so that is how we can calculate. It's very easy. Now one more is there of the similar type question. There we have changed the impurity here only in this solid. Like NaCl is there, same NaCl, but now it is doped with 0.002. Okay, so we have changed the value. Mole percentage of aluminium chloride, so we have changed the cation impurity which is introduced there, that is aluminium ion this time. So you have to calculate the cation vacancy. So again the method is going to be same, that aluminium we know will be having 3 positive charge. So one aluminium ion is going to displace how many sodium ion? 1, 2 and 3. Total 3 are going to be displaced because aluminum is having 3 positive charge. So 3 are going to be displaced to maintain the electrical neutrality of the solid. But the space of 1 is going to be occupied by aluminum ion itself. So only 2 vacancies are going to be created. So the number of vacancy which is going to be created are going to be 2. So total vacancy created by one aluminum ion is how many? 2. So if you introduced 1 mole of aluminum ion, then it will create how many vacancy? It will create the vacancy equivalent to 2 mole. That is 2 mole of Na plus vacancy are going to be created. So 2 mole, when you convert it into Avogadro number, it becomes 2 into 6.022 into 10 raised to power 23. Okay. Now what is the given value of the impurity? That is 0.002 mole percentage. Again, as it is in mole percentage, so we have to convert it into fractional form. So in 0.002 divided by 100, as it is converted into fraction, of aluminium ion, how many cation vacancy will be there? 2 into 6.022 into 10 raised to power 23. Again the same unitary method, multiple of this, that is 0.002 divided by 100, or we can simplify it like 4 into 6.022 into 10 raised to power 23 multiplied by 10 raised to power minus 5. Okay, so we simplify it further, 24.088 into 10 raised to power 18, and finally we have to write the answer in the scientific notation. So it will be like 2.4088 into 10 raised to power 19. So this much number of the sodium vacancies are going to be created when this much mole percentage of the aluminum chloride is introduced in the solid. So that is how you have to solve this kind of question. So the numericals of different types which can come from this chapter already we have finished. So that's all for today. Now in the next video we are going to discuss about the electrical property and the magnetic properties of the solid. So that is going to be the final topics which are left there, and after that the chapter is going to be closed. Okay, so that's all for today. Goodbye students. Please like, subscribe my channel, and don't forget to press the bell icon. See you in the next video.